So this is the 17th Colloquium of Extreme Universe Project. And today we are very happy to have Professor Harvey Reall from Cambridge. And let me briefly introduce him. He obtained his PhD from Cambridge in 2000 and studying under Stephen Hawking. And after spending a few years as a postdoc in Queen Mary and the Kavli Institute for Theoretical Physics, UC Santa Barbara. And in 2005, he was appointed to a lectureship at Nottingham University. And in 2007, he moved back to Cambridge as a faculty member at DAMP and also a fellow of Trinity College. And from 2013, he has been a full professor. And he's been recognized as one of the world leading experts of theoretical aspects of general relativity and gravitation, especially a black hole in higher dimensions. And he has published many influential papers, including a very famous one on a rotating black ring in 5 dimensions. And today he is going to tell us about creases, corners, and caustics, non-smooth structures on horizon. Okay, so Harvey, please start.
Okay, well, thank you very much, Akihiro, for the invitation and for that kind introduction. So this talk is based on a paper that I wrote recently with my my student Maxime Gadieu, and you can find it in this paper here. So I'm going to be talking about event horizons. So let me remind you of some basic properties of event horizons in general relativity. So every point on an event horizon belongs to a null geodesic that lies within that event horizon. So these geodesics are called the generators of the event horizon. So a standard property of these generators is that they cannot have a future endpoint. So once the generator is in the event horizon, it cannot leave the event horizon. So future endpoints are impossible. That follows more or less from the definition of an event horizon. So although generators cannot have future endpoints, they can have past endpoints. So here's an example. This picture shows the Penrose diagram of a black hole formed in spherically symmetric gravitational collapse. And so the yellow shaded region is the collapsing star. In the Penrose diagram, this line here denotes future null infinity. This is past null infinity. And this blue line here is the event horizon in this spherically symmetric space-time. So this blue line consists of null geodesics. These null geodesics do not have future endpoints, but they all have a past endpoint at this red dot here. So this is a Penrose diagram where we suppress some of the dimensions. If we actually look at this red dot in space-time, it looks just like the origin in Minkowski space, and emanating from that red dot are the generators of the event horizon, which look locally, it looks just like a future light cone of this point in Minkowski spacetime. Of course, we can, if we wish, extend these generators to the past so that we get the past null cone here, the purple cone, or on this diagram, it's this purple straight line, which goes back to past null infinity. So there's nothing that stops us extending the generators to the past, and each generator is perfectly smooth. We can extend it to the past, but as generators of the horizon, the red dot is a past endpoint. We can't if we extend them to the past, they no longer lie in the horizon. Okay, so in this talk, I'm going to be discussing aspects of the horizon relating to its lack of smoothness. So one thing I want to emphasize right at the start is that we're going to be assuming throughout this talk that space-time is smooth. So any lack of smoothness is nothing to do with a lack of smoothness of space-time, space-time throughout my talk is going to be smooth. So a textbook theorem about an event horizon is this theorem here. It says that, so H is my notation for an event horizon in this talk. So an event horizon is an achronal continuous hypersurface. So achronal just means that no 2 points of an event horizon are time-like separated. So for example, if we go back to this picture on the right here, on the right, if I pick this point here and this point here, then they are time-like separated. Okay, but this point at the bottom does not belong to the event horizon. If I pick 2 points which do belong to the event horizon, then they cannot be time-like separated. That's what it means for the event horizon to be achronal. The second point here says that the event horizon should be a continuous hypersurface. And I emphasize the word continuous here because that's all that the theorem guarantees in general. So in particular, it does not tell us that the horizon is smooth. In fact, it does not even tell us that the horizon is differentiable. And so the event horizon is not smooth, except in very special cases. And these special cases are cases that are well studied. For example, a time-independent black hole like the Schwarzschild black hole or a Kerr black hole is an example where the horizon is smooth. But in general, the horizon is not smooth. And we've already seen an example, coming back to our figure, the horizon is not smooth at this red dot in this gravitational collapse example. We cannot draw a tangent plane to the horizon at that point. So it's not even differentiable there. So the motivation for this work is to discuss the nature of the non-smoothness of an event horizon. Some time ago, it was pointed out that an event horizon can be very non-smooth indeed. So there exist examples of spacetimes for which the event horizon is non-differentiable on a dense set. So in other words, if you pick a point on the horizon, there does not exist a neighborhood of that point in which it is differentiable. So these examples were constructed by deleting sets of points from Minkowski spacetime, and as the authors of this paper say, the examples are very artificial, and they have certain undesirable features. So, for example, they are either not globally hyperbolic, or they have an incomplete future null infinity. But nevertheless, the examples show what is, in some sense, the most pathological thing possible, which is consistent with the theorem I mentioned a few minutes ago. So another important theorem about horizons is this one here, due to Beam and Krolak. So this one says that an event, if P is a point on the event horizon, then the event horizon is differentiable at P if and only if P lies on exactly one generator of the horizon. Okay, so if P lies on more than one generator, then the horizon is not differentiable there. And again, going back to our example, at this point, there are infinitely many generators passing through this point, and so the horizon is not differentiable there. The second point of this theorem is that if a point lies on more than one generator, then that point is necessarily an endpoint. Okay, so again, we've already seen that. This point here lies on more than one generator, and it is an endpoint of all of those generators. The converse of this statement, though, is untrue. So it is possible to have an endpoint which lies on only one generator. So in this talk, I'm going to use the notation h-end for the set of past endpoints of horizon generators. And we want to understand that set. So we're not the first people by any means to think about this set. And so in particular, I want to mention the work of Shino and Koike from some time ago, who performed a classification of the different types of point that can occur in this set, subject to an assumption of genericity. Okay, so this assumption of genericity is used so that they can apply methods from catastrophe theory to understand this problem. And this leads to a very nice classification. However, I think that there's a question about how this notion of genericity that they used relates to the notion of genericity that one would like to use, which is with respect to perturbations of the metric. So I don't want to assume anything about genericity at the moment. So I'll come back and discuss the work of Shino and Koike again a little bit later. But for now, we will proceed without assuming any kind of notion of genericity. So we'll keep things general. Let's get some intuition for this problem by looking at some examples. So in explicit examples of gravitational collapse or black hole mergers that have been studied in the literature, it is found that this endpoint set is quite simple. So it consists of a two-dimensional space-like set, which is called the crease set. And in these examples, it's found that at the crease set, pairs of generators enter the horizon. So each point of the crease set is a point where two generators enter the horizon. So it's an endpoint of exactly two generators. So the boundary of this set is also part of the endpoint set. And this boundary is a line of caustic points. So roughly speaking, a caustic point is a point at which infinitesimally nearby generators intersect. So anyone who studied GR will know there is a more mathematical definition of caustic points, which are also called conjugate points or focal points, involving Jacobi fields. But I'm not going to use that definition in this talk. So we'll just use the intuitive definition of infinitesimally nearby generators intersecting. So in order to show what this looks like in a picture is difficult because it is difficult to draw pictures of event horizons in 3+1 dimensions. So let's look at the analogous situation in 2+1 dimensions. So in 2+1 dimensions, I've drawn a horizon here. So the blue lines are generators of the horizon. And you can see that these generators enter at this crease set in purple. And at each point of the crease set, two generators enter the horizon. The endpoints or the boundary of that crease set consists in 2+1 dimensions of this pair of caustic points shown by the red dots. So of course, in this 2+1 dimensional example, the crease set is now a one-dimensional set rather than a two-dimensional set. So that's an example of how this looks like in a lower dimensional situation. In 3+1 dimensions, I can't draw a picture of the horizon plus this crease set in a useful way. So I've just drawn here a picture of the crease set. So the crease set is a two-dimensional space-like set, which is shown in purple here. At each point of that set, two generators enter the horizon typically. And the boundary of that set, in simple examples, at least, has the topology just of a disk, and the boundary of that disk is a circle of caustic points. Okay, so this is a more generic example of gravitational collapse than I showed earlier. The earlier example I showed you was spherically symmetric. This shows you what the endpoint set of the horizon would look like without spherical symmetry. So if we break all of the symmetry, we get something like this. Another very nice example we can talk about is a black hole merger. So again, I want to do this in a fairly general situation. So I don't want to consider any kind of special symmetry. So let's consider a black hole merger which is non-axisymmetric. So for example, a merger of two rotating black holes after orbiting and coalescing. So a few years ago, Roberto Emperan and his collaborators came up with a very nice exact model for a non-axisymmetric black hole merger. And so their model applies in the extreme mass ratio limit, where one of the black holes is much, much larger than the other black hole. So in that limit, we can treat the horizon of the large black hole as an infinitely large planar horizon. So effectively, we're treating the horizon of that black hole as a Rindler horizon in Minkowski space. And so when we consider the small black hole falling across the horizon of the large black hole, what we need to do is to find a Rindler horizon in the space-time, the Kerr space-time of the small black hole. So the construction just takes the Kerr solution and constructs a Rindler horizon in it. And the idea being that Rindler horizon then describes the horizon of the large black hole. And we can just then follow the horizon generators backwards in time to see what they do. And this is the picture that you get shown on the left here. So in this picture, the black curves are the generators of the Rindler horizon or the horizon of the large black hole, and the green curves show the generators of the horizon of the small black hole, which you can see are twisting round because this is a Kerr black hole which is rotating. So you can see they merge with the generators with the horizon of the large black hole up here. What's also shown in this picture is a red line, which is perhaps not so easy to see. So let me highlight it. So the red line comes up here, around here, and down there. That red line is the endpoint set of the horizon generators. Okay, and you can see it's twisting round because of the rotation of the small black hole. And it goes along both black hole horizons to the past of the merger. Now, if on the left-hand plot, that just looks like a line, but if you zoom in on that line, you discover that it's not a line, it's actually a two-dimensional set, as I told you it would be a few minutes ago, and that two-dimensional set is shown here on the right. So if you zoom in on that red line, you discover it's actually a two-dimensional strip shown in gray. And the boundaries of that two-dimensional strip, which are these blue curves, are lines of caustic points. So this strip is the crease set, and as I said earlier, its boundary is a pair of caustic lines. Okay, so moving on. So now, what we'd like to ask is what features in these examples are responsible for this simple structure for the endpoint set of the horizon. So that we've seen that it's a fairly simple structure in these examples, but why do they have this? Why does it have this simple structure? And what else is possible? Are more complicated things possible? So we've already seen earlier that there are some very pathological kinds of examples one can construct. So we need to make some assumptions which would exclude those pathological examples. And these are the assumptions we make. So we assume, firstly, that space-time is globally hyperbolic. That's completely reasonable. We need space-time to be globally hyperbolic in order for physics to be predictable in space-time. So that's very reasonable. But we also need this second assumption, which is that the horizon is smooth at late time. So precisely what this means is there exists a Cauchy surface sigma lying to the future of the endpoint set of the horizon, such that the intersection of sigma with H, which we call H star, is a smooth submanifold. So the picture to have in mind here is that we have some gravitational collapse or a black hole merger that produces a black hole. At late time, that black hole will settle down to a Kerr black hole, and at late time, the idea is the horizon will be smooth. It will be a smooth perturbation of Kerr, And that's what this late time assumption means. So in particular, this excludes, for example, space-times where we throw stuff into the black hole at a constant rate, for example, at very late time. So we're assuming everything is smooth at late time. We don't make any assumptions about equations of motion. So everything I say is essentially going to be kinematic, I suppose. It's just using basic properties of Lorentzian causality. So with these assumptions, the first thing we show is that the endpoint set of the horizon generators is related to something, a mathematical object that has been studied previously, which is called the null cut locus of H star. So I'm now going to take a few minutes to explain to you what this object is. Or maybe I should pause to see if there are any questions so far. Okay, I'll continue. So the null cut locus. So this can be defined for any two-dimensional space-like surface. So we can forget about event horizons for a minute and just let H star be an arbitrary two-dimensional space-like surface in an arbitrary smooth space-time. And let's consider null geodesics which are emitted orthogonally to H star. And let's say we emit them to the past orthogonally to H star. So this green curve here is supposed to show H star, and this blue line is supposed to be a null geodesic, which is orthogonal to H star. So locally, at least near H star, this is a null geodesic. It's traveling at the speed of light, and so it's not possible to deform that null geodesic into a time-like curve from H star. However, if we go sufficiently far along that null geodesic, we might reach a point like this red point here, beyond which it is possible to find time-like curves from H star. So this yellow line here is an example of a time-like curve from H star. So if we go sufficiently far along that null geodesic, it might become possible, where there might exist time-like curves from H star. And if that happens, then this red dot, the first point beyond which that happens, is called a null cut point or along that geodesic. The null cut locus is then the set of all of these null cut points for all of the null geodesics emanating from H star in this family. So this purple line is supposed to give some idea of the null cut locus in this example. Now, this is closely related to the notion of a cut locus in Riemannian geometry. In Riemannian geometry, on a Riemannian manifold, we can consider a surface and we can consider geodesics orthogonal to that surface, and we can ask how far along a geodesic can we go before the geodesic fails to minimize length from that surface, and that defines the cut locus in Riemannian geometry. And the Riemannian cut locus has similar properties to the Lorentzian cut locus. So in the Riemannian example, the cut locus is something that's been studied for at least a century. And there are examples in Riemannian geometry of cut locuses which are very complicated. For example, fractal. But not so long ago, at least in the Riemannian geometry sense, it was shown by Ito and Tanaka that although this cut locus can be very complicated, it can be decomposed into parts with simpler structure. Okay, so this is one of the key results that we used in our work. Is we took the work of Ito and Tanaka in the Riemannian context and we transposed it to the Lorentzian setting to understand the null cut locus in a Lorentzian manifold. And so we obtained a Lorentzian analog of their decomposition. So here is the the result. So one more thing I have to tell you about a null cut locus is the following. So any point in a null cut locus is either a caustic point or it lies on at least two generators. So a caustic point here would mean a point which is conjugate to the surface H star or a focal point of H star. So this is a fairly old result about the null cut locus. Any point in a null cut locus is either it's a caustic point or it lies on at least two generators, two of these null geodesics. In particular, if you have a point in the null cut locus that lies on only one generator, it has to be a caustic. So armed with that fact, we can classify endpoints of our horizon, or indeed a general null cut locus, as follows. So in the first category, we put all of the caustic points. So if any point is caustic along some generator, we call that a caustic point. The second category is the non-caustic points. So non-caustic means non-caustic along all geodesics through that point. And we can subdivide the non-caustic points further. So if we have a non-caustic point which lies on exactly two generators, we call that a normal crease point. This is, again, inspired by the Riemannian terminology. If we have a non-caustic point which lies on exactly three generators, we call that a normal corner point. I'll explain why in a moment. And then we consider all the other points in a separate class. So all of the points on more than four generators, or four or more generators, we just put them all together. So we then prove that some of these classes have nice properties. So the nicest part is these two categories here, the normal crease points and the normal corner points. So we prove that, again, following the Riemannian example of Ito and Tanaka, that the set of normal crease points forms a two-dimensional space-like submanifold, which we call a crease submanifold. And roughly speaking, the crease submanifold looks like a self-intersection of the horizon, where two parts of the horizon intersect each other. The normal corner points, we prove, form a one-dimensional space-like submanifold that we call the corner manifold. And this near this submanifold, or at this submanifold, the horizon exhibits a triple self-intersection. So there are three generators through each point of this submanifold. And everything else, so all of the caustic points and all of the points on four or more generators, this is where the complex behavior lives. This is the stuff that could be a complicated fractal, but nevertheless, the size of that set can't be too big. So the dimension of that set is at most one. So this is the Hausdorff dimension, which is introduced to measure the size of a fractal. That can't be any bigger than one. So in particular, this possibly complicated set is a lower dimensional object than the crease submanifold. And so we'll mostly be focusing on this crease submanifold. Okay, so let me explain why we call these creases and corners. So again, the normal crease points form a two-dimensional space-like crease submanifold. The normal corner points form a one-dimensional space-like corner submanifold. So to explain the terminology, let's consider a Cauchy surface sigma, which you can think of as describing an instant of time in the space-time. And let's take its intersection with the event horizon. So this describes a cross-section through the event horizon at an instant of time. So on a cross-section, if sigma intersects the crease submanifold, typically that intersection will be a one-dimensional line. And so we'll see a one-dimensional crease on the horizon. So this is what a crease looks like on a horizon cross-section. It's a place where two smooth sections of the horizon meet each other. So hopefully you can understand why the word crease is appropriate for this structure. Similarly, if the surface sigma intersects the corner submanifold, it will do so typically in isolated points. And those isolated points are corners, like this point here, at which three creases meet. and we have 3 smooth sections of horizon meeting here. So this is like the corner of a tetrahedron or a cube. Okay, so let me now give you an application of some of this. So after we wrote our paper, we were thinking, what can we do with our this crease submanifold? What kind of applications could we have? And this is something that we thought of shortly after finishing our paper. So this is not in the paper, so we'll probably write this up in the fairly near future. So we realized we could apply this to the Busso entropy bound. So let me describe what that is. So a bit of terminology. A light sheet is a non-expanding null hypersurface, which you follow the generators of that null hypersurface as far as possible until you hit a caustic. That's the definition of a light sheet. Let's consider the entropy S crossing some light sheet, which is emanating orthogonally from a 2-dimensional space-like surface sigma of area A. Let me draw a picture of that. So here we have some surface sigma, and then we follow let's say we follow the light sheet from that surface, something like this, say, and we have to follow that light sheet as far as possible until it forms a caustic. And so maybe it does something like that, and there's some complicated caustic down here. Okay, so that defines a light sheet. Then the Busso entropy bound is a conjecture which says that the total entropy crossing this light sheet cannot exceed the area of sigma divided by 4gh bar. Okay, so this conjecture was motivated by an earlier conjecture of Bekenstein. So the Busso conjecture was motivated by trying to make the Bekenstein conjecture mathematically precise. And it's also closely related to the generalized second law of black hole mechanics. So this was initially a conjecture, but there are actually proofs of this result if you make extra assumptions. So, for example, if we take S to be the entropy of matter, and we assume that that matter has some kind of local notion of entropy, a local entropy current, and that current obeys certain inequalities in terms of the energy momentum tensor, which are satisfied by reasonable kinds of matter, then one can prove this result. Okay, so that's kind of a coarse-grained description of this entropy. More recently, Busso and collaborators have obtained proofs of this conjecture, where S is really some quantum or microscopic notion of entropy, some kind of regularized von Neumann entropy for quantum fields in this kind of space-time. So anyway, so what I want to discuss is this idea that when we construct the light sheet, we should keep going until we hit a caustic. So on the picture on the left here, I've drawn a more this is a picture in 2+1 dimensions. So you should think maybe of sigma as being some surface like this, and this orange surface is the light sheet emanating orthogonally from sigma, and it's forming some complicated caustics down here. I'll explain the labeling here later on, but just think of this as some complicated caustic set. And you see a self-intersection here. This is what we called a crease earlier. Anyway, this thing on the left is quite complicated. But there was a proposal by Tavakol and Ellis shortly after Busso proposed his bound that rather than terminating the light sheet at a caustic, we should terminate at what we've called the null cut locus. If you do that, you will obtain the figure on the right. We just have this simpler structure with a crease. So in this figure, the null cut locus is just this line here. You should think of these surfaces extending down the picture. I've not drawn that. Okay, so we could ask, can we use our improved understanding of the null cut locus, which I've described a few minutes ago, to say anything about the Busso bound if we terminate the light sheet at the null cut locus in the way that Tavakol and Ellis proposed? And it turns out that we can. So as I said, the null cut locus is dominated by the crease submanifold, this two-dimensional submanifold. Everything else is lower dimensional. So the only part of the crease, the only part of the null cut locus which carries area is this crease submanifold. And if you combine our discussion of the null cut locus with, for example, this proof of Flanagan-Marolf and Wold, it's very easy to prove a version of the Bousso bound which looks like this. So on the right-hand side, you see the difference between the area of sigma and twice the area of the crease submanifold. And so we see that this geometrically well-defined object, this crease submanifold, is playing a role here in the Bousso bound. The factor of 2 here looks a little bit surprising at first, but that just arises from the fact that the map from sigma to the crease submanifold is 2 to 1, because by definition, every point of the crease submanifold lies on two null geodesics. Okay, so that was an application. Are there any questions? Okay, let me continue. So let me now change direction slightly and discuss perestroikas. So what I want to talk about now is how the horizon evolves in time. So to discuss time, we need to introduce a time function. So we'll call that tau. A time function is just a smooth function on space-time whose level sets are space-like submanifolds. So and they're Cauchy surfaces, I should have said. So we have a time function on space-time, and the surfaces of constant tau, which I'll call sigma tau, are Cauchy surfaces. So then the intersection of sigma tau with the event horizon h, we can think of as describing the event horizon at time tau. Okay, so that's what that intersection describes. And if this surface sigma tau passes through the endpoint set of h, then this intersection will not be smooth. It will have some arrangement of creases, corners, and caustic points. Now, as tau varies, then this arrangement may undergo a qualitative change at a critical value of tau. And if that happens, we call this a perestroika. So this word comes from the catastrophe theory literature. It comes from the work of Arnold and collaborators. So this is a word, this word means restructuring in English. So it seems like an appropriate description of this phenomenon. So in particular, if we think about the kind of horizon we discussed earlier on, of a horizon formed in gravitational collapse, where we had the crease submanifold. This was the kind of picture we drew earlier. That's our horizon. If we consider our foliation by surfaces of constant time, like that, eventually we're going to reach a surface which is tangent to the crease submanifold, this red line here. And clearly that point of tangency is when there is some qualitative change happening on the horizon cross-section. And so that's an example of a crease perestroika. So a crease perestroika occurs at a time tau when sigma tau is tangent to the crease submanifold. So we wanted to understand what kinds of physical situation this describes. And so we analyzed the situation as follows. So near this point of tangency, the event horizon is locally, just looks like a union of two intersecting null hypersurfaces. So I told you earlier that near the crease submanifold, the event horizon looks like an intersection of two null hypersurfaces. And so if we introduce Riemannian normal coordinates around this point, then we can just describe the event horizon by writing down the equations for two intersecting null hypersurfaces in those coordinates, and thereby determining an exact local form for the behavior of the event horizon near this point of tangency. And it turns out there are three qualitatively different possibilities, which I shall now describe. So when I describe them, I'm going to shift my time function so that this point of tangency occurs at tau equal to 0. So the first example I'm going to show you is the one associated with this picture. So this is going to be tau equal to 0, and slightly positive tau is going to look like this. So this will be positive tau. Down here is negative tau. Okay, so this is what I'll now show you. So that looks like this. So for we call this the flying saucer, for hopefully for obvious reasons. In fact, the word flying saucer is something that's been used previously in the catastrophe theory literature, which has seen examples like this in other contexts. So what this describes is the nucleation of a component of event horizon in a generic gravitational collapse. So at time 0, a 0 size portion of event horizon forms, and for very small positive tau, the horizon cross section looks like this. It looks like an intersection of two smooth sections. Each smooth section has the form of, locally looks like a paraboloid, and the intersection of the two paraboloids is this crease running around the equator of the flying saucer. So we have an exact mathematical description of this that we can use to calculate geometric properties of this object. So for example, we can show that the length of this crease scales as the square root of tau for small tau. The angle between these two smooth sections of horizon, that also scales in the same way. And the area scales proportional to tau. So as to reiterate, this describes the nucleation of a component of event horizon in any generic kind of gravitational collapse. So we saw a very special kind of gravitational collapse at the start of this talk, where everything was spherically symmetric and the event horizon was immediately smooth once it formed. This is actually what happens in gravitational collapse, is that at the instant of collapse we form a tiny flying saucer. We might form multiple flying saucers in the collapse process, and they will then merge as and grow and merge. Okay, so the second kind of perestroika that arises in our classification describes the collapse of a hole in the horizon. So in examples of gravitational collapse or a black hole merger, there are some choices of time function, some choices of foliation of the space-time, which can give a brief period where the topology of the horizon is toroidal. Okay, so this is a very brief period typically, but it's been seen in various examples. And what happens when you have this brief period of toroidal topology for the horizon is that the hole in the torus rapidly collapses. In fact, it collapses superluminally. And then the horizon becomes topologically spherical. And so this instant at which the hole collapses is described by another perestroika, which I've shown here. So on the left, this is the horizon with the hole in it just before the collapse. So the black hole region is the region outside the red surface on the left. The red surface again looks locally like the intersection of two smooth surfaces. Again, these are paraboloids. And again, we see a crease, this green line running around the inner edge of the hole. So when we have this hole in the torus, there's always a crease running around its inner edge. And so this then collapses, and the instant of collapse at tau equal to 0 looks like this. So this yellow section of this figure shows new generators which have entered the horizon between this picture on the left and the one in the middle. And then for positive tau, these two smooth sections of horizon move apart. The black hole region is the region in between these two surfaces. And now the horizon will have developed spherical topology and is smooth in this example. So again, we can calculate geometrical properties of these surfaces for small tau. And again, you find that the length of this crease scales as the square root of minus tau. As does the angle between these two smooth sections on the left before the collapse. Incidentally, the reason the hole collapses superluminally is because the crease submanifold is space-like, so that's immediate. Okay, so then there's one other kind of perestroika, which describes, for example, a black hole merger. So in this perestroika, we have two locally disconnected sections of horizon, which are shown on the left. So the black hole region is the region over here and over here, so to the left and to the right of those two surfaces. So that these could be parts of two different black holes. Each of the surfaces has a crease, shown in green, and those creases have the shape of hyperbolas. So that's for tau negative. At tau equal to 0, those two creases merge together, the hyperbolae fuse into a pair of straight lines, and we get this figure in the middle. So this figure in the middle is showing the instant of merger of the two black holes. The orange section here shows new generators which have entered the horizon between the figure on the left and the figure in the middle. And then for positive tau, the horizon expands transverse to the merger point into a bridge which now connects the two black holes. So now the black hole region is the region going through this tunnel. Again, the lighter color here, this yellow, is the new generators which have entered the horizon between the figure in the middle and the figure on the right. And you see on the right that this bridge connecting the two sections of horizon again has a crease running along its two edges. So after the merger, so what happens is these creases just reconnect. And so before we have hyperbole, after we have hyperbole. And so we claim this describes the instant of merger of any generic black hole merger in nature. Okay, so this is the merger process always involves creases reconnecting in this way. And again, you can use the local geometrical description to calculate properties of these surfaces. For example, that the angle at the creases here or here scales again as the square root of tau.
Sorry, could you tell us about the difference between this orange region and the yellow region? I have just missed.
Yeah, good. So remember, creases are endpoints of horizon generators. So creases are places where new generators enter the horizon.
Yes.
So because we have a crease on the left, some new generators have entered when we go from the left picture to the middle picture, and those new generators are shown in orange. Now in the middle, we still have creases present, these two green lines, and so more generators are still entering the horizon. And
so the new generator entering the horizon still creates a crease set.
It's entering at the crease set. So at each point of the crease set,
at the crease set. I see.
Yeah. So you can see that there are two roughly speaking, at each point of the crease, two generators. One goes up and one goes down. So there's one up here and one down here.
I see. I see.
And so similarly over here we have a crease, we have a crease in the middle. So some new generators enter between the middle and the right, and those are shown in yellow. The existing generators are also expanding, which is another effect, but that's a much smaller effect. The new generators entering is really the dominant effect here.
Okay. Thank you.
Are there any other questions? Okay. So let me now come back to this issue of genericity or stability. So let's ask the question. So we've studied the structure of the set of endpoints of horizon generators in general, but there's another question we could ask, which features of this set are stable if we make a small perturbation to the space-time. So for example, in spherically symmetric collapse, we saw that the endpoint set is just a single point, this caustic point we saw right at the start. And if we perturb that space-time, if we break the spherical symmetry, then in the perturbed space-time, the endpoint set will now have a non-trivial crease submanifold. Okay, so that means that the original structure, this single caustic point, was unstable, because when we perturb it, we get something more complicated. Okay, so there's a natural question to ask, is which structures of the endpoint set are stable or generic? And that was what was investigated by Shino and Koike in this work I mentioned earlier. Again, assuming this particular mathematical notion of genericity, which is the notion required to apply methods from catastrophe theory to this problem. And what their classification gives is there are some similarities with what I described earlier, but there are also new features or different features. So firstly, if you look at non-caustic points, then generically, according to their classification, these lie on, these are either points of double, triple, or quadruple self-intersection of the event horizon. So these double self-intersections are what we called, they form what we call the crease submanifold. The triple self-intersections are what we call the corner submanifold, and the quadruple self-intersections were the stuff that we didn't care about. But at least generically, those are there. If you went on to consider quintuple or higher self-intersections, they would be non-generic, and that's why they don't appear in this list. The more interesting, perhaps for us, is the second classification, which is of the caustic points. So remember, when I discussed caustic points in our work, all we could say is that they form a set which is not too big. We couldn't really say very much about them. But if you use these methods of catastrophe theory, then you can actually say exactly what kinds of caustic point they are. And in the terminology of catastrophe theory, these caustic points are called points of type A3, which I'll describe in a moment. And they lie on lines in space-time. So remember, I said that the set of these points can't be more than one-dimensional. And generically, according to Shino and Koike, it's exactly one-dimensional. So these caustic points lie on lines in space-time. As I mentioned earlier, there is an outstanding issue here, though, which is that this mathematical notion of genericity is what they had to assume to make progress on the problem. But there seems to be a gap between the notion of genericity that's used here and the notion of genericity that one would like to use physically, which is genericity with respect to perturbations of the metric. So, but we haven't got anything to say about that, so I won't discuss it any further. But we'll just proceed with assuming this is all fine. Okay, so let me show you what these A3 caustics look like. So as I said, these A3 caustic points, generically, they live on space-like lines. And so if we consider a cross-section through the horizon, then we'll take a cross-section through one of these lines, and that will give us isolated A3 caustic points on a horizon cross-section. So in order to visualize that, it's convenient first, instead of considering the horizon, let's consider the horizon where we extend the generators to the past beyond their past endpoints. So we're considering a bigger surface. And let's consider a cross-section of that. That looks like this figure on the left. Okay, so we saw this earlier, in fact, but now earlier we were describing a null surface in space-time. Now we're describing a space-like surface corresponding to a cross-section through this extended event horizon. So this is what the A3 looks like. The A3 point, this isolated caustic point, is this point here. But you can see emerging from that point is this structure here. This is the famous swallowtail structure from catastrophe theory. So you see the surface has a self-intersection along this crease, and then there's this structure with these cusp-like features along these edges. So you see this cusp here and here, which are labeled A2s on this figure. So we have emerging from the A3 point, we have a crease and this feature with cusps. But as I said, in order to obtain this figure, we had to extend the horizon generators beyond their past endpoints. If we're only interested in the horizon, then we don't want to extend beyond the past endpoints, and that gives us the figure on the right. And you can see that to go from the left to the right, we had to truncate this feature. We had to cut off the tail of the swallow to give us this figure on the right. And so on a horizon cross-section, this is what a caustic point looks like generically. We have an isolated caustic point, and emanating from that point is a crease, a self-intersection of the horizon. And the crease, the angle at the crease, this angle here, tends to pi as we approach the caustic point. And so the horizon smooths out as we approach the caustic. And so on a horizon cross section, a caustic point is an end point of a crease generically. So creases end at caustics. Now, if we go back to the figure on the left, I mentioned these A2 caustics. So an A2 caustic is a simpler kind of caustic than an A3. It's just a cusp. And A2 caustics certainly occur in the real world, and they occur on null surfaces, as shown on the left. But in the classification of Shino and Koike, there's no A2s. So a natural question is, why don't they occur on horizons, as it seems they cannot? And so we couldn't find a simple answer stated anywhere for that. And so we looked into this in some detail. And it turns out that if you have an A2 caustic, then these two sections of surface which meet at the cusp, it turns out they're always time-like separated. So an A2 caustic cannot occur on an achronal surface, and that's why they don't occur on event horizons. So the only kinds of caustic that appear on event horizons are A3s. So because the A3s live on lines, we can again consider what happens when our surfaces of constant time happen to be tangent to this line, and that defines what we call an A3 perestroika. So we studied these in detail and classified what they describe. And there are two cases. So the top row here shows the first case. So time runs from left to right. So the first type of A3 perestroika, we have a finite section of crease in green, and that crease has two A3 endpoints, these caustics endpoints. As time evolves, the crease shrinks to zero, and the two caustic points just annihilate, leaving behind a smooth section of horizon. So the crease is gone and the caustics have gone. So that's the first type of A3 perestroika. The second type is on the bottom row here. Again, we start off with a crease on the horizon. And now at a certain time, zero here, we nucleate an A3 caustic that immediately splits into two, and the two caustics move apart and leave behind them a smooth section of a horizon in between them. Okay, so in the first case, we destroy crease by annihilating a pair of A3 caustics. In the second case, we destroy crease by nucleating a pair of A3 caustics. But in both cases, you see that the A3 perestroika has a smoothing effect on the horizon. And this, in fact, is the process by which horizons become smooth. So remember, we're assuming the horizon is smooth at late time, so all of the creases and so on have to eventually disappear. And this is how they disappear, through these processes involving caustic points. Okay, so I'm going to end with a couple of more speculative points related to things I've discussed. So this is completely changing direction. So let me first discuss the possibility that creases make a contribution to black hole entropy. So creases are a well-defined geometrical structure on a horizon of a dynamical black hole, so maybe they could contribute to entropy. And there is reason to think that they might, coming from aspects of entanglement entropy in quantum field theory. So there's an old idea, which I don't have time to explain in detail, that some or all of black hole entropy arises from the entanglement of quantum fields across the horizon. So in particular, there's an idea that entanglement entropy is a divergence quantity, but it was pointed out that one can absorb that divergence into a renormalization of Newton's constant, such that when you add the entanglement entropy to the bare Bekenstein-Hawking entropy, the result is a finite generalized entropy. So that's quite an attractive idea. Now, it's also known that if we consider a surface in flat space which has a crease in it, and we consider entanglement entropy across that kind of surface, then there are new features that arise from the crease. So there's a new kind of subleading divergence in entanglement entropy arising from the crease. And so if you combine these ideas, that suggests that maybe creases might contribute to black hole entropy. And the form of the contribution should look something like this. So this is we imagine we have a cross section of the horizon which has a crease. So the suggestion is that there is a contribution to entropy of the form of a line integral along the crease, divided by the Planck length, 1 over root g h bar, of some function of omega, where omega is the angle between the two smooth sections of horizon which meet at the crease, and L is just the proper length along the crease. So this function f here is sensitive to the particular quantum fields which are present in the space-time, but it does have some universal features, which were in particular discussed in this paper by Hirata and Takayanagi. In particular, one feature is that f has a pole at omega equal to 0, and so the integrand diverges as omega goes to 0. Now, this term here is inversely proportional to the Planck length, whereas the Bekenstein-Hawking entropy is inversely proportional to the square of the Planck length. And so this is a sub-leading term compared to Bekenstein-Hawking. And so in general, it's going to be much smaller than Bekenstein-Hawking. Furthermore, at a crease, new generators enter the horizon, and those generators expand and increase the area. So whenever there is a crease present, the Bekenstein-Hawking entropy is necessarily growing. And so it's hard to see how we could ever test this idea. In particular, it's hard to test because this f, we don't know much about it, apart from a few universal properties. However, surprisingly, there is one way we can test this idea, which is to consider this collapse of the hole in the horizon that I described earlier. When we had a torus-shaped horizon with a crease running around the hole in the torus, that crease will make a contribution to the entropy like this. And as it collapses, the length of the crease tends to 0, but also omega tends to 0. And so this pole becomes important. And the scaling I told you about earlier is such that this quantity remains finite as tau tends to 0. Once the hole is collapsed, there is no crease present, and so there is no crease entropy. And so this contribution is therefore discontinuous at tau equal to 0. And so we can now ask, so over a sufficiently short period of time, this discontinuity is going to dominate over anything that happens in the Bekenstein-Hawking entropy. And so we can ask, is this discontinuity consistent with the second law of black hole mechanics? Does the entropy increase discontinuously? And so that requires that the residue of this function f at omega equal to 0 must be non-positive. And so that's a non-trivial, well, that has to be true in order for this suggestion to actually respect the second law. It was a bit unfortunate that we didn't then go on to check whether this f has to be positive in the examples coming from quantum field theory. But when I gave this talk somewhere else last week, someone asked this question, and so I did go and check whether f is positive, and it looks like indeed this sign agrees with the sign that you get from entanglement entropy in quantum field theory. So it seems to be consistent. Okay, so I'm aware I'm slightly out of time, so let me briefly tell you my final speculative idea, and then I'll finish. So this concerns the Gauss-Bonnet term in black hole entropy. So in four-dimensional standard GR, we can add to the Euler-Hilbert action. We can add, to the Einstein-Hilbert action. We can add a Gauss-Bonnet term to the gravitational action. This is a term which is topological in 4 dimensions, so it does not affect the equations of motion. However, it has been argued that the Gauss-Bonnet term makes a contribution to black hole entropy. So even though we haven't affected the equations of motion, there is a change in the formula for the entropy of a black hole, and there's now this new term present where H is a cross-section of the horizon, mu is the induced metric on the horizon, and R of mu is the Ricci scalar of that metric. Gamma here is the coefficient of this Gauss-Bonnet term. Now, if the horizon cross-section H is smooth, then this integral evaluates just to the Euler number of H. That's a topological invariant of the horizon cross-section. So it's 4 pi times that invariant. So this is a topological term on a smooth horizon. But as we've been discussing, dynamically, horizons are not smooth. So how do we make sense of this on a non-smooth horizon? Well, one way we could make sense of it is to regulate this integral by defining it as a limit of smooth surfaces which converge to this surface H. So since those surfaces are smooth, this topological formula will still hold, and so it will hold in the limit. Okay, so that's a way of defining this term so that this topological result still holds for a non-smooth horizon. However, of course, the topology of the horizon changes in black hole formation or in a black hole merger, and it changes in opposite directions in those two processes. And so it was pointed out by Sudipta Sarkar and Aaron Wall some time ago that means that the only possibility that's consistent with the second law is gamma equal to 0, because otherwise this discontinuity would lead to a violation of the second law in either black hole formation or a black hole merger, looking over a sufficiently short time interval near the merger or formation. However, I'd like to point out there's another possibility, which is that is to ask, does this integral actually need regulating on a smooth horizon? So if the horizon is not smooth, can we make sense of this without this regulation procedure? And the answer seems to be yes. So if we think about the various kinds of non-smooth features which appear on horizons, we have these creases and corners. Near a crease or a corner, the horizon is piecewise smooth, and so there's no problem defining this integral, perfectly well defined. Similarly, at an A3 caustic point, at an A3 caustic, this Ricci scalar diverges, but we showed that, in fact, it does so in an integrable way. So this integral still exists for an A3 caustic. And so this is therefore well defined on a non-smooth horizon, even without having to regulate it in the way that I described earlier. So although it's well defined, it's no longer topological. Okay, so this integral just then varies continuously through a black hole formation or a merger. And so this argument that it violates the second law is no longer applicable. Nevertheless, if we look at it more closely, we found that this term still varies very rapidly in a black hole merger, for example. And so we can still argue that gamma here has to vanish, but only if there are no higher order terms present in the entropy. So if we think of the Bekenstein-Hawking term, that goes like the inverse square of the Planck length. This goes like Planck length to the power 0. A higher order term might be Planck length squared. If there are higher order terms, Planck length squared or higher, then this argument no longer works because it becomes sensitive to those higher order terms. And so it seems that if you do have such terms, which you would if you think of this entropy in an effective field theory sense, then there's no reason to exclude this Gauss-Bonnet term because this argument no longer works. And so it seems to us that at least in an effective field theory sense, if you define this term in the way I've just described, just as a regular Riemann or Lebesgue integral, then there's no problem with it. Okay, so I'm very sorry I've overrun by a few minutes. So I'm just going to put my summary slide up now and I shall stop speaking. Thank you for listening.
Okay, thank you. Thank you very much. Okay, so it's time for questions and discussion. So if you have any questions or comments, so please just unmute your mic and ask questions, please.
Can I ask a question?
Please.
So I have thank you very much. Really beautiful talk. Hello, yeah. So I am very curious about this also final part of this your new contribution to entropy. And my question is that so you are this 1 over square root g scaling something quite new to me. And could you explain why you have this kind of 1 over square root g?
Yeah. So it relates to. Yeah. So as you know, in 4 dimensions, the area law in entanglement entropy goes like 1 over epsilon squared, where epsilon is the cutoff.
Yes.
The crease, and that's balanced by a UV divergence in 1 over g, the Newton constant. So that there's a contribution to 1 over g, the running of the Newton constant going like 1 over epsilon squared. Now these creases, again, as you know, in 3+1 dimensions, the crease contribution scales like 1 over epsilon. Okay, so in order to balance that, we need a 1 over square root. That's where that's coming from.
Actually, so on the other, so we have some holographic, calculation of this entanglement entropy. And that case, actually, 1 over always, we are computing some classical area. So it's like 1 over G Newton factor appears.
Mm-hmm. So, this is in the bulk, you mean?
Including also our work, actually. So divergence is really, it's really a square of this area of divergence. But also there are, coefficients in front of divergence, like, degrees of freedom or central charge. And so this leading all the area of term and also this corner, I think probably you may mean some corner contribution where we have some kind.
That's right. Yes. So again, there's a possibility of a corner contribution.
Yes.
So I'm aware people have discussed that as well. So we could make similar suggestions about a corner contribution to
yes.
But we found that seemed to be less well studied when we were looking at that. But
I see.
Yeah.
So but if you do theory calculation, this corner contribution also proportional to central charge, and so area term and corner term is scaled same way, and so that's the reason we usually think it's 1 over G. So I think
but I guess that's because you're thinking of things using the holographic dictionary.
Yes.
The central charge.
Yeah. And it's probably
this idea of Susskind and Uglum.
I see. Yeah.
Something a bit different, isn't it? It's looking at the running of the Newton constant as you vary the cutoff. I don't know. I'm sure someone has attempted to relate. In fact, Roberto Emperan, I think, has a nice paper where he applies some Randall Sundrum type setup to relate those two ideas, I think. But I'm afraid I've forgotten the details. But I think it's a slightly different idea.
I see. Thank you very much. I understand it. Very beautiful result.
I have a question. So you mentioned about some perestroika of this crease set, and that actually for the same structure, maybe this depends on the choice of slices. Is that correct? And yes. I'm wondering if your notion of this contribution, a crease contribution to the entropy, is that also a slice-depending notion or independent?
Yeah, it's slice dependent, but of course, so is the Bekenstein-Hawking entropy. I mean, the whole thing is defined for a particular slice through the horizon, isn't it? So it's it's always slicing dependent in that sense.
Okay, then how about this? You also mentioned in the earlier stage about Bussell bound, some area, some -2 area of the crease. Is this? You have now the stringent constraint on the entropy. Is this also a slice? Depending on the choice of slices?
No. This is not slicing dependent. So this is so we set off. We have some surface sigma, and we just consider its past null cut locus, which is a geometrically invariant. Well, it's a geometric invariant in space-time. So maybe I should stick to my color coding I used earlier. So here we have our null GD6 coming from sigma, and at some point they will fail to minimize. They will be. You can deform them into time-like curves, and then we'll get some null cut locus here. This is the crease submanifold. And so that's a geometric invariant. So that was why we started thinking about this, is because this crease submanifold is a geometric invariant. It should have some important role in physics, and so this was one place where it seems to where it's natural to think about it. So that So there's no slicing dependence here.
Okay, I see. Thank you. Nomura-san, go ahead.
Hi, I can't turn on the video. This is a late night here in US. Hey, so you have this bound, yes, on this page, because now, did you use this Flanagan-Marov word assumption to show this? But if that's the case, if that's the case, you can cut the null sheet anywhere, right? And then the bound is A minus the area of the place where you cut. Then of
That's
course
right,
this
yeah.
result is just a limit that you can make that to be to the crease, right?
Yeah, I mean, it's very simple to take their argument and get this, but
Yes,
as
just to take a limit and a special case. Or
Yeah,
of course,
yeah.
it's just a limiting case. But is it true?
Yes,
As you said,
I
this
mean,
two just coming from two sheets. So
that's right. There's no work involved in proving this. So as you say, you just take their proof, and yeah, you can. They would take a cross section like this, and as you say, if you take a limit where this other cross section approaches the crease submanifold, which they didn't do, then indeed the answer just pops out, but immediately. So it's yeah, it's there's no work involved in proving this, but our interest is mainly that it emphasizes the geometric role of this object, this crease submanifold.
okay, yeah, great, thanks.
Any other questions?
Can I ask a question?
Please go ahead.
In the middle of your talk, I think you said the angle of the crease increases. I mean, scales with square root or tau. And what is the reason for this square root?
Okay, I guess you can see it if we think about the geometry of this surface, for example. This flying saucer, you can think of it as the intersection of two paraboloidal surfaces. So they look like this. And so this crease is running around the intersection. Okay, so that's what the surfaces look like. And they're moving in opposite directions. So they're moving like that. Okay, so if I evolve that backwards in time, you see that this figure on the left, this is time 0. That corresponds to when these two surfaces are just touching each other. Okay, so they're tangent here, and because they're tangent there, the angle is what's the angle, omega, and the angle is going to 0 here because they're tangent at this point. So that's the reason for the scaling. So it is literally this square root of tau just comes more or less immediately from this figure.
I see. So this scaling is universal for any kinds of crease.
Yeah, that's why it was the same in all of my examples, is because it's always the same kind of thing. We just have two surfaces intersecting each other, and then moving apart so that they become tangent. And yeah, there's a universal behavior when you have that situation.
I see. Thank you.
Yoshina-san, go ahead.
Thank you very much for your interesting talk. I have a question about the classification of the path endpoints of the horizon. You classified the path endpoints, and you comment on the case where the 4 or more null geodesic crosses on that point at that point, and you comment that in that case there might be a fractal structure, right? And do you have a specific example for the property of?
Actually, yeah, I'm not sure whether the fractal structure arises from here. I think it's more likely to arise from the caustic set. So in this set here, we have to put the caustic points and these points with 4 or more generators. And I think it's probably the caustic points which have the fractal structure. But I'm not totally certain.
Okay.
So there are examples that have been constructed. There's an example of, so this is in Riemannian geometry. There's an example of a Riemannian metric on a 2-sphere, which gives a caustic set, which is an example of what's known as a non-triangulable. It's a non-triangulable set. But it's in that example that it looks like infinitely many well, let me try and draw it. Here's a sphere. And so this is all Riemannian, just to emphasize. Let's say we shoot geodesics from the South Pole.
Mhm.
Then the crease set, sorry, the cut locus, sorry, looks something like this. There are infinitely many line segments,
Mhm.
all emanating from this point up here.
Oh, I see, I see. Mhm.
And I think, yeah, and so I think that infinite set may well, I'm not certain about this, but there are aspects of that thing which look kind of fractally to me. But I think the crease submanifold here is still well defined, but it has infinitely many components, infinitely many connected components. It would be the interior of all of these line segments would be the Riemannian version of the crease submanifold.
Thank you very much.
Okay.
Any other questions? Okay, if not, then it's good time to stop the questions. And thank you, Harvey. Thank you for very nice talks. And let's thank the speaker again.